Okay, here's the recording in progress. Share the screen. Okay, so we're getting near the end. Some of you may have already caught this, but I got a numbering issue here on the notes. So quiz 10 on Friday. So this can't be 10, obviously. So the day before Thanksgiving is quiz 11. Make that 11. And Friday 12/3 is the last quiz. That'll be quiz 12. Okay. And that'll be it for the quizzes. All right, so again, I'm quite a bit ahead. So I'll probably finish early. Most of the rest of the semester will probably finish early, do what we need to do and go from there. So let's see, we were still supposed to do 11/6 on the schedule. I'm totally done with 11/6 and I can finish 11/7 today, maybe sneak in a little bit of 11/8, but we'll see how it goes. Okay, so on the schedule, this is all messed up. Make this quiz 11 and quiz 12 is here. Okay. All right, so we're just still determining do sequences converge or diverge and going from there. Okay, so let's continue on where we were. Okay, so problem 23 on section 7. Okay, so we're doing some of these. Summation of tangent 1/n. All right, so tangent 1/n, notice the lazy notation, not putting the n equals 1 to infinity or whatever, that's okay, depending on circumstance. All right, so tangent is sine over cosine, so sine 1/n, cosine 1/n. Okay, now, we looked at this before, sine of 1/n, we compared it to 1/n. How about cosine 1/n? Remember, n is going to infinity. So when n is going to infinity, well, this thing approaches cosine of 0, which is 1. So sometimes I can pretend it's like this. Well, in a previous section, we did sine of 1/n. We compared it to the harmonic series 1/n. So the comparison series is summation 1/n. So I'm looking for a limit comparison test. All right, so now I take the limit of the ratio, limit n approaches infinity, sine of 1/n over cosine 1/n divided by 1/n. Okay, this cosine 1/n is allowed to slide down. Okay, you might recall a property of algebra. I've used that several times. You have a over b divided by c. Well, you're allowed to just slide the b down, a over bc, like so. Okay, so a divided by b divided by c. Several ways you can look at it. One easy way is to multiply top and bottom by b, and this would cancel out, and this would give me bc. Another way to think of it is if you divide by c, you multiply by 1 over c, so you have a over b times 1 over c, and it ends up looking like that. So I slide this down, and then I choose to link these two together and this together. Okay, so the limit of a product is a product of the limits. So I separate out limit n approaches infinity of 1 over cosine 1/n. I already know that's 1, right? Direct substitution, so to speak. Plug in a super big number. 1 over a super big number is practically 0. Cosine of 0 is 1. Okay. And if you look back at a previous section, we saw that this was also 1. Okay. You can do L'Hopital's rule for that. So it's 1 times 1, which is 1. So in other words, in the long run, whatever happens to this also happens to this. And what do we know about summation 1/n? That diverges because that's our harmonic series. Okay, so therefore the series S also diverges by limit comparison tests. And so this thing diverges by limit comparison tests. All right. Okay, 31. Summation 5 to the k over 3 to the k plus 4 to the k. This is kind of weird. Okay, now, if I only had one of these in the denominator, I would say that the series diverges. So suppose I didn't have this one, right? It doesn't matter if you have k or n, same thing. So 5 to the k, 3 to the k, that's a geometric series where the common ratio is 5/3. So we would say the series diverges. Likewise, if I only solve this, 5 to the k over 4 to the k, that's 5/4 of the k. That diverges. But I have two of these. Okay. And they're sort of combining. Do these two combine? Is that sufficient to take care of this? Okay, I guess, only analogy is you've got, big brother and two little brothers, right? Can the two little brothers gang up to handle the third brother, so to speak? Okay, so which is bigger, 5 to the k or the sum of these two? Clearly 5 to the k is bigger than this, and 5 to the k is bigger than this. But what if they're together, they're double teaming, so to speak? Okay, double team here. Okay, you sports people, common theme, right? If somebody on the other team is too good, then you double team them, right? Put two people on them, and maybe that'll neutralize that person. Okay, well, let's take a look. Okay, 3 to the k plus 4 to the k is less than 4 to the k plus 4 to the k. Okay, so 3 to the k is certainly less than 4 to the k. I add 4 to the k to both sides. And this can be written as 2 times 4 to the k. Okay, then I do the reciprocal. So by the reciprocal rule, 1 over 3 to the k plus 4 to the k is greater than 1 over 2 times 4 to the k. So by the reciprocal rule, I just flipped this thing. That one with that one. Reciprocate and you have that. Then multiply both sides by 5 to the k. In other words, I get what I want. So I have 5 to the k over 3 to the k plus 4 to the k is greater than 1/2 times 5 to the k over 4 to the k. And that's the key thing, idea right now. So what do I want to say about this one? So 1/2 summation 5 to the k over 4 to the k. The 1/2 doesn't affect convergence or divergence, right? We can write it as 1/2 summation 5/4 of the k. That's a geometric series. So how do you know? Just plug in. Plug in 1, 5/4. Plug in 2, 5/4 squared. 3, 5/4 cubed. You say, oh, I keep multiplying by 5/4. So it's a geometric series. It's divergent. So r is equal to 5/4. R is greater than 1. Okay. So we've established that this series diverges. This series has terms bigger than this one. So therefore, the original series also diverges by comparison tests. Okay, so that was a strategy for this one. So yes, indeed, 5 to the k is still bigger than both of these combined. Okay, these two combined in strength or power, whatever, it's still not enough to offset the 5 to the k. It's hard to tell offhand, but you can try. I don't know if the calculator goes that high, but you can try 100. 5 to the 100th divided by 3 to the 100 plus 4 to the 100. The 5 to the 100 still wins. Okay, so this was a strategy for this one. So I got it to be not just two different bases, but one base, so to speak. Okay, so I wrote it like that. So 3 to the k is less than 4 to the k. Add 4 to the k both sides. This can be written as 2 times 4 to the k. Do the reciprocal rule. So I want to establish a series which is bigger than something which diverges. And this one I established that it diverges. So, okay, so the bigger series, the smaller series goes infinity. So for anything above it goes infinity. That would be like you're richer than a rich person. If you're richer than a rich person, you're also rich. Okay, if you're poorer than a rich person, you can't say anything. You still might be rich, you might be poor, you might be penniless, you might be middle class, right? But if you say that person is rich and say, oh, that person is richer than that person, that automatically makes them rich, so to speak. Okay. All right, so that's a little bit of an interesting one. Okay, the last one I was going to show you was 33. Then I'm actually done with the section. I'll introduce a new section, but I won't get started with it too much. Summation n over n plus 1 raised to the n squared. Okay, and I look at that and say, oh, I can take the nth root of that pretty easily. So I'm going to aim for the root test. Okay, so I'm going to take the nth root of this thing. So n over n plus 1 to the n squared, nth root. And if you take the nth root, it's like raising to the 1 over n power, as you can see right here, which I'm going to do. Okay. Yeah, strictly speaking, you're supposed to have bars, but these are all positive quantities, so I can afford to kind of leave it out. All right, and then this will become a power of a power. I multiply n over n plus 1 to the n. Okay. Now, we saw a little while back that n plus 1 over n to the n approaches e. Limit n approaches infinity of n plus 1 over n to the n was e. Look back in your notes. We did that a little while back. So what if we flip it? 1 over e as n approaches infinity. Okay, that's 1 over 2.7. That's less than 1. So therefore, the series is absolutely convergent and therefore convergent by the root test this time. Okay, so we did the root test. Okay. All right, so that's as much as I was going to do from 11.7. I will give you the introduction to 11.8, but it now looks like, I can mark this off, we only have 4 sections left. Okay, so we have plenty of time to finish everything. So I'll introduce 11.8, then we're going to quit. Okay, in fact, the rest of the week, my quota was just to go up to 11.8, so I can do that, tomorrow and Friday still, hopefully, then 11.9 the next week. Yeah, but we'll see how it goes. Okay, so what is going on with section 8 now? So we're getting very close to the end. We have something called power series. Power series, page 746, looks like this. Look at number 1. Summation n equals 0 to infinity Cn x to the n. And now, for most of the rest of the chapter, as I was mentioning earlier, we're going to index beginning at 0. That's not absolute. That's not all the time. But quite often, we're going to introduce the series beginning at 0. The c's are coefficients Cn x to the n. So C0 x to the 0, x to the 0 is 1, plus C1x plus C2x squared plus C3x cubed. An easy way to think of it is a polynomial of degree infinity. Okay, so I'm just writing my book. Infinite polynomial. Okay, so if I stop at C0, say that's constant. If I stop there, it's linear, like y equals mx plus b. If I stop there, that's a quadratic, squared. If I stop there, it's a cubic. Well, imagine that it never stops. You have an infinite polynomial with coefficients. Okay? You say, well, how do you do that? Well, it depends on what x you choose. The series might converge or diverge, right? So it's a function of what x you plug in. Okay? So this is sort of like what we have over here with all of this stuff. But all of this stuff, notice there's no x anywhere. There's no variable per se. Now we're going to introduce an x. Okay, so make it a little bit harder. You say, well, how do I know if it converges or diverges? It depends on the value of x. Okay, now, a little bit tricky thing here. By the way, if you want to put this on your cheat sheet, you may. box number 1, the so-called power series. Please notice a dot, dot, dot. We are used to stopping somewhere. This one never stops. Goes on forever. X to the million, X to the billion, X to the trillion. It just keeps going on and on and on. Okay. Now, we are also going to see some series of this type. So look at box 3. You may want to copy that down. It looks like instead of X, they got X minus A to the whatever. X minus A squared, X minus A cubed. Okay, that's called a power series centered at A, or a power series about A. Sometimes it's actually more convenient not to have X, but to have X minus A, like X minus 2, X plus 5, and so on. Okay. So if this was X minus 2, we would say centered at 2. Or if it was X plus 5, we would say centered at negative 5. And so on. You don't have to write any of that down. We'll see that. Okay, so an example number 2, I can get it here. Okay, summation n equals 0 to infinity of x to the n. 1 plus x squared plus x to the n. Okay, so that's a simple infinite polynomial. So a power series can be thought of as an infinite polynomial. All the coefficients are 1. So you say, well, does it converge or diverge? It depends what you plug in for x. Okay. So if I plug in a half, I get 1 plus a half plus a fourth plus 8. That's a convergent geometric series. But if I plug in 2, 1 plus 2 plus 4 plus 8, that diverges. Okay, so this power series, we would say is centered at 0. I mean, that fits the pattern of what we had before. Where you don't have that parenthesis stuff, this is centered at 0. That's, of course, what we like. Maybe I'll write that down also. So centered at x equals 0. And if you want to put that on your cheat sheet, you may. Centered at x equals 0. That's the nicest case. Not so nice is when we're centered somewhere else on a number line. Where we go x minus a to the first, x minus a squared, x minus a cubed, fourth, and so on. Okay. So the question is, how do we know whether this thing converges or diverges? Very nice theorem. 749, we will not prove it, we'll just state it. For a given power series, summation n equals 0 to infinity. So again, we're starting to have our series begin at 0 in general. Cn x minus a to the n. There are 3 possibilities. Okay, so let me cover this up for a moment. And let me just think. Okay. What happens if I plug in a? Well, they're all 0, except maybe the first term. So I definitely have convergence at x equals a. Back way over here. Box 2, or number 2. I'm dead sure it's going to converge at 0. If I plug in 0, it's 1. 1 plus an infinite number of zeros, it's going to stay 1. If it looks like this, x minus a, it's sure to guaranteed to converge if I plug in a. Right, let's suppose it's at x minus 2 everywhere, x minus 2, x minus 2. Okay, if I plug in 2, it's going to converge because everywhere there's going to be 0 except for that one. It might turn out that's the only point of convergence. So box 4, you can put the whole thing on your cheat sheet if you wish. 3 possibilities. The series converges only when x is equal to a, wherever it's centered. So it's not possible to say it never converges. You guarantee convergence at one number, a, right? You can tell right away if I plug in a, everything cancels out. Possibility 2, the series converges for all x. Okay, number 3 is actually what happens most of the time, quote unquote. There aren't going to be that many homework problems where this is true or this is true. Most of the time it's this one. There is a positive number r, it's called the radius of convergence, such that the series converges with absolute value of x minus a is less than r, diverges if absolute value of x minus a is greater than r. Okay, what that means is starting from the center, you go a certain amount to the left and to the right, same amount, left and right, and that'll give you an interval of convergence. Okay. Here's such a picture, figure 3. Okay, I don't have any more hands. I'm using 2 hands to hold the book up. I'll try to put the book down, but well, maybe go like that. Okay, so we're centered at A. We have a so-called radius of convergence. I go r to the left and r to the right. So everywhere here, I have convergence. In fact, absolute convergence. Way out here and way out here, you have divergence. And then at the 2 endpoints, anything goes. It might converge, it might diverge at the 2 endpoints. You generally have to check the 2 endpoints. So if you look over here, all of these are possibilities. It could be open, 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 close, close, open, close, close. Okay. So how do you know? You just have to plug it in. So it says here, anything can happen. The series might converge at one or both endpoints, or it might diverge at both endpoints. Okay. Which means there's actually 4 possibilities. Okay. So when you have your radius of convergence, I know a lot of this is all nebulous right now, it doesn't make any sense until we do some problems. Okay, so we're centered somewhere. All right, so first, it might converge only for that number, in which case we would say the radius of convergence is 0. It might converge for all real numbers, in which case we would say r is infinity. You go infinitely far to the left and to the right. But the quote unquote usual thing is you have a radius of convergence r. You go that same distance left and right. So let's say the radius of convergence is 2. Then you go 2 to the left, 2 to the right, open circle temporarily, open circle temporarily. So right here, you have absolute convergence. Way out here, divergence. And then the 2 endpoints you have to check separately. That's usually the way the game works. That will lead to an interval of convergence. So radius convergence. I know radius sounds funny, but if you think of the one-dimensional analogy, that makes perfectly good sense. Now in 2 dimensions, right? How do we talk about radius? We have a circle, right? You're given a point, then you say, okay, go 5 units every direction. You go that way, that way, that way. So you have a circle. 3 dimensions, you understand, right? When you get to Calc 3, 3-dimensional stuff, okay, you get a sphere. So start from a point in space and say the radius is 5. Okay, go 5 that way and that way and that way and down and right and that way, and you get a sphere. Well, imagine in 1 dimension, which is just a number line, I want to use the word radius. Okay, I go 5 units, quote unquote, every direction. Well, there's only 2 directions. I either go to the left or to the right. So it does make sense in the one-dimensional sense to say the radius is 5. Okay, I go 5 each direction, of which is only 2. Okay. In 2 dimensions, you can go that way, that way, that way, right? And you get a circle. And in 3 in space, you can go that way, then you get a sphere. Okay. So here, if I go 5, the radius is 5. Every direction, there's only 2 directions, either left or right. Okay. All right, so let me show you the problems. Maybe show you just one, then I'll be done. So what are we supposed to do? 11.8, 3 through 27. So maybe I'll just show you how one of them goes. Page 751. Sorry, I have to raise the book up in order to show it. So those of you who don't have the book, obviously if you have the book, just look in the book. Sorry, that's the best I can do because it's up against the arm of the document camera, but I think you can read 19 and then before that. And 21. And I think the last one was what, 27? So it's all there. Okay. Most of the time we'll be doing the ratio test. Okay. So I think I'll just show you one. I still have tomorrow and Friday to finish the section, and that was par for the course, so to speak. Okay. Let's look at the language. So I'll do number 3. Find the radius of convergence and interval convergence of the series. Radius of convergence, interval of convergence. How do you do that? Summation n equals 1 to infinity, -1 to the n x to the n. They're starting at 1. By the way, if they started at 0, you would still get 0. And just for fun, I wrote out some of the terms. So this alternates. I plug in 0. Well, I'm not plugging in 0, but I put it in anyway. If I plug in 1, it's negative. So I have negative x. Plug in 2, 2x squared, minus 3x cubed, plus 4x to the 4th. Okay, so here's my infinite polynomial. Stop here, so y equals negative x. Oh yeah, linear. Stop here, sure, quadratic. Cubic, 4th power. Well, imagine you never stop. Just go on forever. And I'm going to plug in some numbers, like plug in 2, plug in 0.5, plug in pi. So, well, how do I know if it converges or diverges? Let's find out. So let's take the ratio test. So absolute value of a sub n plus 1 divided by a sub n. Now, this particular series doesn't have a fraction. So remember where I said, okay, we have to do the flipping and all that stuff. You don't have to here because there's no fraction. Okay, ignore the -1 stuff. Remember, -1 to the n or n plus 1 or n minus 1. It's either going to come out to be 1 or -1, but if you put the bars, it's always 1, right? Absolute value of 1 is 1. Absolute value of -1 is 1. So you can just drop the bars generally. Okay, and then, so forget about this. N plus 1, x to the n plus 1, divided by a sub n, just copy the original. Okay, so that's n plus 1 over n. X to the n plus 1 divided by x to the n is just x. And that approaches absolute value of x as n approaches infinity. When n gets big, this is 1. If I plug in a billion and 1 divided by a billion is essentially 1. So we approach absolute value of x. Well, what do we know about the ratio test? This converges if absolute value of x is less than 1. So that automatically tells me the radius of convergence is 1. Okay. So on my number line, I lay down the 0, which is where we're centered. This is centered at 0. So how do you know if you're centered somewhere else? It would have to be parentheses x minus 2 or x plus 8 or something like that. Okay. And I go 1 unit to the left, 1 unit to the right. Okay, so everywhere in here, absolute convergence. Everywhere here and here, divergence. Yeah, I already know I have radius of convergence is 1. Okay, what happens here and here? Got to try it. So I plug in -1. So plug -1 right there for x. It's -1 to the n times n times -1 to the n. Well, -1 to the n times -1 to the n is 1 to the n. That's just n. So summation of n, that diverges by the test for divergence. A sub n's do not approach 0, right? 1 plus 2 plus 3 plus 4 plus 5, that blows up. How about if I plug in the other endpoint, x equals 1? Put a 1 there. Well, 1 to the n is just 1, so I can just ignore it. So I have summation -1 to the n times n. That also diverges by TFD, test for divergence. And so what's test for divergence? If a sub n does not approach 0, the series diverges by test for divergence. And again, watch out. If a sub n does approach 0, no conclusion. Okay. So some of you in the previous quiz said, oh, a sub n does approach 0, therefore the series converges. No, that's not true. Okay. And our famous example, quote unquote, again, was the harmonic series. The harmonic series, the a sub n's do approach 0. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. right? Those a sub n's approach 0, and yet that series blows up. It approaches infinity. All right, so in this particular case, they both stay open. So final answer, R is 1, radius of convergence. I start at 0, I go left and right 1 unit, and the interval of convergence is parenthesis -1, 1. Okay, so I don't include -1, I don't include 1. Okay. Right, so the series will converge for -1, 1. In fact, you can now think of this as the domain. If you now regard this as a function, this infinite polynomial, you will get convergence if x is between -1 and 1. And if you're outside of that, the series will diverge. So if I plug in 0.5, this series converges. If I plug in 3, the series diverges. That's what this is talking about. Okay, so that's what we're up against. I just decided to show you one. We'll do many more tomorrow and Friday. So we should finish in plenty of time. So I should be up to 11.8 by Friday, which I wasn't even supposed to finish until next week. So we're way ahead, I suppose. So I can afford to slow down and end early like today. Okay, so I'm done, folks. We'll do more of these tomorrow. Let me stop the share and see if there's any questions. And if not, we'll quit. Okay, so any questions, please? Chat. All right, then have a good day, and we'll see everybody next time. Okay, all right, bye, everybody.
Take care, Professor. Thank you.
Okay, thank you.